I'm Carlo Angiuli, and this is the long talk for Internalizing Representation Independence with Univalence. Representation independence theorems tell us under what conditions we can evolve a library without breaking its dependence. While the details of these theorems differ across programming languages, the basic idea is usually about the same. Suppose a language has some interface mechanism, or some way of equipping an abstract type with some operations. For example, we may have an abstract type of queues equipped with enqueue and dequeue operations. Now suppose we have two implementations of queues. Representation independence says that these two implementations are equivalent if we can exhibit a binary relation between the underlying types that respects the operations. In the case of queues, this means that the two empty queues must be related. If two queues are related, enqueuing the same thing onto both must give us related queues. And finally, if two queues are related, either both are empty, or dequeuing gives us the same element and another pair of related queues. These results are usually formulated as metatheorems. The classic example is system F, where representation independence is a consequence of parametricity. By defining a correspondence between two elements of existential type, we can establish an observational equivalence between those elements and conclude that any client will compute the same answer regardless of which implementation it uses. But if our language has dependent types, we could do better. Ideally, we would like to know internally, as a theorem stated and proven inside the language itself, that related implementations are actually equal. That way, we can use representation independence to transfer formalized proofs between related implementations. This problem has been studied in the context of the Coq proof assistant, where it's known as proof transfer. There, one often wants to consider multiple representations of a mathematical object to optimize either for proofs or for computations. For example, the unary natural numbers are ideal for proofs because their induction principle is mathematical induction. But if a proof has large arithmetic subgoals, it can be impossible to discharge these in a reasonable amount of time without switching to a more efficient representation. While this work has been useful to formalizers of mathematics, it doesn't quite solve the problem at hand. Cubical relies on a parametricity translation to transfer results across program and data refinements, but it can't transfer dependently typed goals. Recent work on univalent parametricity relies on univalence, an idea from homotopy type theory, and while it can handle dependency, it can only transfer results across isomorphisms, so there are many cases of interest that it doesn't cover. We can see this already in the case of queues, which can be represented as a single list where you enqueue on the front and dequeue off the back, or as a batched queue, a pair of lists where you enqueue on the front of the first list and you dequeue off the front of the second list. And if the second list is empty, then you reverse the first list and use it as the second. Every queue has a unique representation as a list queue, but many possible representations as a batched queue depending on where the queue is divided. So while we do have a correspondence that respects the queue operations, it's not a one-to-one correspondence, also known as an isomorphism. Instead, it's a many-to-one correspondence, that is, a function. In our paper, we show how to combine univalence and higher inductive types, two ideas from homotopy type theory, to internalize a relational representation independence theorem in Cubical agda. After introducing Cubical agda, I'll explain how univalence lets us prove invariance under structure-preserving isomorphisms, a result known as the structure identity principle. Then, I'll show how we generalize the structure identity principle to structure-preserving functions using a higher inductive set quotient. Finally, I'll summarize our main result, which generalizes this again to the case of arbitrary structure-preserving relations. So what is Cubical agda? It's a recent extension of the agda programming language that implements features from homotopy type theory in a computationally well-behaved way. If you want to check it out, I recommend starting with the Cubical agda library in development on GitHub, where you can also find all the results from this paper. In any system with dependent types, including agda, type checking requires figuring out whether terms are equal. This is usually handled by splitting term equality into two different relations. The first is called definitional or judgmental equality. Definitional equality is handled silently and automatically by the type checker and includes alpha, beta, and some eta equalities. The remaining equations are called propositional. These are marked explicitly in terms and are mediated by the identity type. Besides being a congruence, the most important fact about the identity type is that if two types are equal, then they're isomorphic. We can cast between those types and the casts cancel. This works all right, but the identity type has some well-known shortcomings. For example, you can't prove that pointwise equal functions are equal unless you add that principle as an axiom. But axioms don't interact well with definitional equality because they don't reduce, and for the same reason, they disrupt the proofs as programs correspondence of constructive logic. Cubical AGDA has a different version of propositional equality, which is defined in terms of a primitive interval I that has two constants I0 and I1. Using this interval, we say that a function f from I to a is a proof that f of I0 and f of I1 are equal elements of A. To get an intuition for what's going on, let's replace I with another two-element type, the Booleans. A function from bool to A is exactly the same as a pair of elements of A, f of true and f of false. But unlike bool, we prevent pattern matching on the elements of I, and as a result, I0 and I1 are completely indistinguishable according to the logic. Similarly, while functions I to A determine two elements of A, these elements are likewise always indistinguishable to the logic, which is to say they're always equal. Using the interval, we define propositional equality in cubical AGDA as the path type, written A0 triple equals A1, whose elements are functions from I to A that are A0 on I0 and A1 on I1. It's easy to see that this relation is reflexive by considering constant functions out of the interval. Unlike in ordinary type theory, we can also show that pointwise equal functions A to B are equal by observing that functions from I into A arrow B are the same as functions from A into I arrow B by swapping the order that we abstract the variables. There's also a heterogeneous version of the path type that expresses that two terms of different types are equal, modulo the fact that their types are equal. These dependent paths are just dependent functions out of the interval, again with specified endpoints. Using dependent paths, we can say that two elements of sigma AB are equal when their first projections are equal in A, and their second projections are heterogeneously equal in B, over the fact that their first projections are equal in A. This is more direct than in ordinary type theory, where we would usually say that second of x is equal to second of y after you cast second of x from the type b of first of x to the type b of first of y. To cast between types in cubical AGDA, we use the transport primitive, which says that a path between types A and B gives us an isomorphism between A and B. Voevodsky's univalence axiom is basically the eta law for transport, and one of the main innovations that started homotopy type theory. It says that not only does transport give us isomorphisms, but in fact every isomorphism arises as a transport. Concretely, we say there's an inverse to transport, a function called UA that turns any type isomorphism into an equality, and transporting across UA gives us back the isomorphism. Univalence was originally added to type theory as an axiom, but in cubical AGDA it's a definable function and it computes. In fact, making univalence compute is the main motivation behind cubical type theory in the first place. The subtlety is that types can be isomorphic in more than one way. Think about the Booleans, which are isomorphic to themselves in two ways. So in the presence of univalence, there can be multiple reasons why two types are equal, and the reason you choose can affect what answers you get. When we use univalence, it's useful to stratify types based on how complicated their equality relation is, or how many times you have to iterate equality before it becomes trivial. We say a type is contractible if it has exactly one element. A type is an H proposition, like empty or unit, if its path types are contractible. Most of the types you know are H sets, because their path types are H props. Any two elements are either not equal or equal in a unique way. But remember, the universe is not an H set. In this talk, I'll gloss over some issues related to hlevel. You can read more about them in the paper. Actually, I've already glossed over one. If we define isomorphism as a pair of functions that cancel, then being an isomorphism isn't an h-prop. So we actually phrase everything in terms of a better definition called equivalence. We can also control equality, and therefore h-levels, using higher inductive types. This higher inductive type is the propositional truncation of A, which turns A into an h-proposition by collapsing all of its elements. Here, the first constructor includes the elements of A into its truncation, and the second constructor equates any two elements of the truncation. But how does it make sense that the squash constructor is a path, since usually constructors have to land in the type itself? Well, a path in the truncation of A is a function from I to the truncation, so we can think of squash as really being a 3-argument constructor of the truncation, rather than a 2-argument constructor of a path. We can define maps out of a higher inductive type by pattern matching on the constructors, just as we do for ordinary inductive types. To define the functorial action of truncation, we essentially just send every element bars of x to bars of f of x, and every path squash between x and y to a path between f of x and f of y. In this paper, we also use the set quotient higher inductive type, which takes a type A and a binary relation R on A, and produces an H-set, which is the quotient of A by R. The elements of A mod R are the elements of A, but where any elements related by R are equated by the second constructor. The last constructor, squash, is needed to ensure that any two ways of equating elements are the same. As before, if we unfold the type isSet, we see that it produces an iterated path in A mod R, so the type of the squash constructor is again sensible. So let's get back to representation independence. In dependent type theory, we can express types with a structure as sigma types. For example, a Q implementation is a pair of a type, called the carrier type, and a triple of operations on the carrier, giving us the empty Q and the NQ and DQ operations. So the question is, if we assume univalence, when are two elements of Q equal? Let's start by ignoring NQ and DQ, so we just have a carrier type and an element of the carrier. Suppose we have two implementations of this interface, A with A0 and B with B0. Two pairs are equal when their first components are equal, and their second components are equal modulo the equality of the first. But by univalence, an equality of types is an equivalence, and being equal modulo that equivalence is the same as applying it. Putting this all together, if these two pairs are equal, that means we have an equivalence between A and B, and if we apply that equivalence to A0, we get B0. And that's exactly what it means to be a structure-preserving equivalence for the structure of having a point, namely, you preserve the choice of point. This idea is known as the structure identity principle, that univalence implies that equalities of structured types are the same as structure-preserving equivalences. But to make this idea precise, we have to say exactly what we mean by structure-preserving equivalence, and actually what we mean by structure, too. We didn't come up with this idea. It's been formulated in a number of ways by a number of different authors. One of the main differences is whether they define structure-preserving equivalences directly, or as invertible structure-preserving homomorphisms. In this paper, we do the former by formalizing a cubical version of Martin Escardo's version of the structure identity principle. Specifically, we say that a structure is just a function S that takes types to types, sending a carrier type to the type of S operations on it. An S-structured type, or an implementation of S, is a dependent pair of a carrier type equipped with S operations. Given two S-structured types and equivalence between their carriers, we can ask whether that equivalence respects the given S-structures. A notion of respecting the S-structure corresponds to a predicate over this data, and we write iota for predicates like this. A notion of S-structured equivalence is univalent if having an S-structured equivalence is the same as having an equality of S-structured types. In other words, iota is univalent if the structure identity principle holds, for the definition of structured equivalence given by iota. Then, the structure identity principle says that the natural notion of S-structured equivalence is univalent for a wide range of signatures, including all the signatures built up from this grammar, like elements of the carrier, constant types, products, functions, and maybe. We use the reflection machinery in AGDA to automatically match structures against this grammar and return for a particular structure the appropriate notion of structured equivalence and a proof that it's univalent. These proofs are built up compositionally by looking at the structure of the structure. So, for the structure of having a specified point that we talked about before, if we have two pointed structures A, A0, and B, B0, and an equivalence between the carriers, then F is structured exactly when it sends A0 to B0. If we have a product of two structures, and both have a univalent notion of structured equivalence, then an equivalence is structured for the product exactly when it's structured on the first part and structured on the second part, and so forth. Finally, adding axioms to a structure preserves univalence, so long as those axioms are H propositions. This lets us encode algebraic structures like monoids, groups, and rings by splitting them into two parts, the operations and the laws. For a monoid, the operations are just an identity element and a multiplication. The usual laws say that multiplication is associative and the identity is a unit. But to make sure that these are H-props, we also require that the carrier is an H-set. Axioms also let us capture laws for data structures, such as the fact that you can reorder NQ and DQ operations so long as the queue isn't empty. But while this does hold for list queues, it actually doesn't hold for batched queues because DQ can cause the queue to rebalance. This is the same reason that the correspondence between list queues and batch queues wasn't an isomorphism. The equality of batch queues is just too fine. It exposes internal state that can't be observed by clients. Our key idea is that we can use a structure-preserving correspondence between implementations to tell us when two batch queues are supposed to be the same. Then, we can use a set quotient to equate two batch queues when they correspond to the same list queue, and because this correspondence preserves the queue operations, the original NQ and DQ functions of batched queues will descend to the quotient, and the resulting implementations will be equivalent. In this case, we equate two batched queues when they differ only by where the midpoint is located, and because NQ and DQ respect this quotient, the quotiented batched queues continue to be an implementation of the queue interface. Then, using the structure identity principle, we observe that the original structure-preserving correspondence between list queues and batched queues turns into a structure-preserving equivalence between list queues and the quotiented batched queues. Now, in the queue example, we're able to improve the correspondence to an equivalence by changing the equality on one side, the batched queues. That's because the relation is one-to-many. The list queues already have the right notion of equality. In the general case, the correspondence is many-to-many, and in fact, in some cases it has to be many-to-many because there's no implementation of the data structure that represents each state uniquely. An example of this would be finite multisets, where the type of elements has no ordering. In these cases, we have to quotient both sides to get an equivalence. But when is this possible? In the literature on representation independence, a condition called zigzag completeness occasionally pops up, which states that if x is related to y, x prime is related to y prime, and x prime is related to y prime, then x is related to y prime. Zigzag completeness captures a heterogeneous version of symmetry and transitivity, ensuring that the correspondence gives rise to a well-behaved notion of sameness on each side. Note that one-to-one and one-to-many relations are always zigzag complete. We refine this notion a bit in our work, introducing something called a quasi-equivalence relation, a relation that's zigzag complete, h-prop valued, and where every element of each side is related to at least one element of the other side. Any quasi-equivalence relation between A and B induces an h-prop valued equivalence relation on A, written R left arrow, that relates two elements of A exactly when they're both related to the same element of B. Symmetrically, we get a relation R right arrow on B. Then, we can set quotient both A and B by these induced equivalence relations, and when we do this, R turns into an equivalence between A mod R left arrow and B mod R right arrow. This answers the first half of the question, when can we turn a relation into an equivalence? But to achieve representation independence, we want to know when we can turn a structured relation into a structured equivalence. As before, given two S-structured types and a relation between their carriers, we define a predicate rho saying when this relation is S-structured. We have some technical conditions on these predicates called suitability that essentially make sure that being structured is preserved by passing to a quotient. Then, we say that a suitable notion of structured relation is univalent when it's restricted to one-to-one relations, or to be precise, the graphs of equivalences. It produces a univalent notion of structured equivalence as before. Then, our relational form of the structure identity principle says that the natural notion of S-structured relation is univalent for the signatures built up from this grammar. This is very similar to the previous grammar, except that we have a positivity restriction on the structures that can appear on the left-hand side of an arrow, captured by the second production rule of the grammar on this slide. Combining the results of the previous few slides, we get that S-structured quasi-equivalence relations between A and B induce equalities of the quotients of A and B, viewed as S-structured types. As before, we use reflection to match structures against this grammar, and in the paper we show how to apply this result to the case of finite multisets. Summing up, we're able to obtain internal representation independence results for structured relations in dependent type theory using several ideas from homotopy type theory. Univalence tells us that structured equivalences induce equalities of structures, a result known as the structure identity principle. We identify conditions under which set quotients allow us to turn structured relations into structured equivalences, allowing us to apply the structure identity principle. And all of this computes properly because we're using Cubical Agda. You can visit this URL to see our full formalization, and thanks for watching.